Right. Welcome to the session, and this is week 11 of our NPTEL live discussion on principles of signal estimation for Mimo OFDM wireless communications. And today we are going to discuss week 11, where we'll be seeing MMSE estimation in a multi-antenna transmitter setting and further in a MIMO system. So MMSE Bayesian estimation in a MIMO setting. But before that, we have a doubt which we received in the forum, and I will be taking that. So this is the uh, week 10, uh, question 5. So this which we discussed in the last week. So I'll again redo it. So we have been given that yk is h times vk, and vk is distributed as a Gaussian random variable with mean theta and variance sigma square. Okay, so since we have this, so in this setting, what will be expectation of vk? Right, what will be expectation of vk? So expectation of vk comes out to be h plus theta. Okay, it is very straightforward. And variance of yk comes out to be sigma square, right? So yk is distributed as a Gaussian variable with mean h plus theta and variance sigma square. So this is the distribution of yk, that is each observation, right? Now let y tilde be defined as y minus theta. Okay, so this is a new random variable which we are defining, and if we subtract theta from y, so y tilde will basically be a Gaussian distribution, but now the mean is only h, right? And variance remains sigma square. So if my mean still remains h, what does that mean? That is y tilde is basically some h plus v tilde, right? Where v tilde is now zero mean sigma square variance Gaussian. Okay, try to understand what we did. So basically, y, we initially had a, symbol y in which the noise was mean shifted, and we modified our observation y to y tilde such that my noise is now zero mean, and the variance is still sigma square. So basically our main aim is to bring the noise to zero mean sigma square variance. Okay. Now, if you see this equation, y tilde is h plus some v tilde, and it is now equivalent to y tilde. Now this is at a single for one time instant. Okay, for one time, say k. Okay. So for all case, okay, for all case where k is from 1 to n, we'll have basically a vector, right? So y tilde vector will be vector 1 times h plus v. Okay, so this is my vector 1 is basically a vector of all ones. This is from 1 to n. So it is having n times ones. Okay, and this is equivalent to x times h plus v. Okay, now if you remember the what all do we need, right? So we need to compute h at MMSE, and this is our expression. As you can see, h at MMSE is basically x transpose y over sigma square plus mu h over sigma h square divided by x transpose x over sigma square plus 1 by sigma h square. Okay, so this is what we. So first we need to compute x transpose y. Okay, so what will be x transpose y? It will be one vector times y tilde vector. And what is that coming to be? So it is basically one vector times y minus theta. Okay, is what we have. So if you see, this becomes y minus n theta. Okay, this is basically y minus n theta. And similarly, x transpose x will be basically 1 gets multiplied with 1 n times, so it is n. Okay. So h hat MMSE. So to compute h hat MMSE, if we plug in all the values, okay, in this expression, so we basically have y minus n theta over sigma square plus 0 because mu h is 0. It is given in the question, and we have n by sigma square plus 1 by sigma h square, which is our required answer. Okay. All right. So what next? So I will be solving for week 11. Okay. If you still have doubts, you can just post it in the forum, and we'll take it up in the next week. But make sure that you post everything, because next week will be the last class. Right? So post all your doubts and we'll take them all. So consider LMMSE, which we have in computer linear minimum mean squared error, multi-antenna channel estimation problem for n transmitted pilot vectors, and n received symbols y1 to yn. Okay. And my channel vector defined by hk, and the channel coefficients have sigma h square variance, IID Gaussian. All right. And so what is the LMMSE estimate of h? So this is a straightforward question. So as discussed in the lectures, this is RHY, RYY inverse times y. Okay. So if you see, this will be sigma h square x transpose sigma h square x transpose plus sigma square I inverse y, and this is basically, if you just rearrange it, so this will be sigma h square sigma h square x transpose x plus sigma square I inverse x transpose y. Okay, so this option is B. Option B. So this is straightforward from the lectures. Okay. Right. Question 2. So again, we need to see the LMMSE for a multi-antenna channel estimation problem, and we have been asked what is the error covariance of the LMMSE estimate. Okay, so what is the error covariance? Error covariance for LMMSE estimate of H. So it is basically as from the lectures. So it has been derived in the lectures, 1 by sigma square x transpose x plus 1 by sigma h square I. It was okay. So this is option A. So this is straightforward, okay, directly from the lectures. All right, question 3. So right, again, multi-antenna channel estimation. So all right, we need to find out the LMMSE estimate of H. Right, so first let us construct the X matrix. So this will be 2, 2, 2, minus 2, minus 2, 3, 1, 2. This is my X vector as given in the question, and my Y vector is 1, minus 2, 3, minus 3. Okay, so what is my LMMSE estimate? So if I just write it as h hat L, which is what we need to compute. So this is sigma h square, sigma h square x transpose x plus sigma square I inverse x transpose y. Okay, so we need to solve for this expression. Okay, so let's solve for this expression. So first let me do x transpose x. And okay, so before that, sigma h square is minus 6 dB, and this is equivalent to 1 by 4 in watts. So now I think you know how to convert dB to watts. So I think you can do that. Similarly, sigma square is given as minus 3 dB. And so this is basically half. Okay, this is basically half. Okay, you can use calculator to do these conversions. So, okay, and X transpose X is basically, let's do that. So 2, 2, 3, 2, 1, minus 2, 2 times 2, minus 2, 2, 2, minus 2, 2. And if you solve this, you will be basically getting 4 plus 4 plus 4 plus 4. Okay. And the second will be minus 4, 6, 2, minus 4. Again, minus 4, 6, 2, minus 4, 4, 9, 1, 4. Okay. And this is basically 16, 0, 0, 18. Okay, so this is my X transpose X. So if I plug all the values for H hat estimate, LMMSE estimate, so we will basically get 1 by 4. Okay, 1 by 4, 16, 0, 0, 18 plus half 0, sorry, 1, 0, 0, 1 inverse, and this is 10 minus 11. So I think this we have some space constraint here. See. So X transpose Y is basically 10 minus 11. Okay. So you can just do that. It is straightforward. So due to lack of space, I've just written. Okay, so this comes here. Okay, X transpose Y, which is my third term. And if we solve this, we get 1 by 4, 2 by 9, 0, 0, 1 by 5, 10 minus 11. And if we solve this comes out to be 5 by 9 minus 11 by 20. Okay, this is what we have. And this is option B. Any doubts? Any doubts? Feel free to stop me. Okay. So question 4. All right. So now in this question, it is similar to the previous question, build up, and we need to find out the ML estimate of H. Okay, so it is again straightforward. So ML estimate of H we did long back, which was the Moore-Penrose pseudo inverse, if you remember. So H hat ML is X transpose X inverse X transpose Y. Okay, so and we solved for X transpose X in the previous question. X transpose X was 16, 0, 0, 18, right? And so X transpose X inverse will be basically 1 by 16, 0, 0, 1 by 18. And X transpose Y we solved as 10 minus 11. And we just need to multiply this. So H hat ML is 1 over 16, 0, 0, 1 over 18. Okay, multiplied with 10 minus 11. And if you multiply it, you will be getting 10 by 16 minus 11 over 18. Okay, so this is option C. Right. Any doubts? Okay, no doubts. Right. Question 5. So multi-antenna channel estimation. We are given n is 4 pilot vectors. And again, the x and y vector are similar to the previous two questions. And sigma h square is minus 6 dB and sigma h square is minus 6, which is equivalent to 1/4 in watts, and minus 3 dB is basically 1/2. Okay. And the error covariance. So we have asked what is the error covariance. Okay. So in the lectures, it has been derived. So error covariance is given as expectation h hat minus h hat minus h transpose, and this expression is x transpose x over sigma square plus I divided by sigma h square inverse. Okay, so this is the expression which has been done in the lectures, and we'll just plug in the formulas. So what is x transpose x? So x transpose x, we saw it was 16,0,0,18, as we saw in the last two examples, and sigma square is basically 1/2 plus identity for 2/2 case. So this is 1,0,0,1, and sigma h square is basically 1/4, right? And we'll take its inverse. Okay, so let's solve this. So this is basically, so the 2 will get multiplied, okay, inside. So this will be 32,0,0, and the 6 plus, similarly the 4 gets multiplied. So you have 4,0,0,4 and inverse of this. So this is essentially 32 plus 4, which is 36,0,0,40. Okay, and its inverse. So this is 1/36,0,0, 1/40. Okay, this is my required answer, and this is option D. Any doubts? Okay. Question 6. So, all right, this is a different problem. So we are given a Mimo channel estimation problem. Okay, so fine. So we have now multiple transmit antennas, and now we have multiple receiver antennas also. So let's write the X vector. Okay, so we have 2, minus 2, 2, 3, 2, 1, minus 2, 2. Okay, and we are given that n is 4. Okay, so n is 4. So this is my n is 1, n is 2, n is 3, and n is 4, right? So this is basically my transmit antenna 1. This is transmitted by transmit antenna 2. Okay, so we know that now, seeing the pilot, we know that it has 2 antennas. Right? Our system is having 2 antennas. Let's build the received side. So you see the received side, we have 1, minus 2, 1, minus 2, 1, 3, minus 3, 1, minus 2, 2, minus 3, minus 1. And if you see, this is n is 1, n is 2, n is 3, and n is 4, right? And this is basically my receive antenna 1, receive antenna 2, receive antenna 3. All right. So we have been asked what is the size of the MIMO system. So this MIMO system is basically having 2 transmit antennas, and we are having 3 received antennas, right? So this is a 2 cross 3 or 3 cross 2 system. So you see we have a 2 cross 3 system. So generally we have R cross T is our notation, but in the options here 3 cross 2 is not given, so we are going with 2 by 3, 2 cross 3. Okay, so any doubts? Okay, no doubts. We move ahead. Question 7. So this is a follow-up to the previous question, and right. So, we are asked that the covariance matrices RHH of the channel and of the noise are what? Okay, we need to compute these covariance matrices. Okay, so let's do this. So the covariance matrix RHH of the channel. Okay, this is basically expectation of H transpose. Okay, and as done in the lectures, this is R sigma H square I 2 by 2. And so R is basically my number of receive antennas. Okay, and so if you solve this, this becomes 3 times sigma H square is minus 6 dB, and this is basically 1 by 4 in watts. So this is 3 times 1 by 4 times I 2 by 2. Okay, so this is my RHH. And similarly, my covariance matrix for the noise RVP is computed as expectation VV transpose. Okay, and as done in class, this is R times sigma square I 4 cross 4. So be careful of the variance which you use, right? So noise variance and the sigma H square are separate, right? So one is the AWGN and another is the fading noise. So be careful of that. So again, this is 3, which is my number of receive antennas, and sigma. So like we computed sigma H square. So similarly, sigma square is given as minus 3 dB, and this is basically 1 by 2 in watts. How we will do that? 10 to the power minus 3 by 10. So this is 3 times half and I 4 cross 4. So this is your RVV. So if you see the options, we have 3 by 4 I 2 cross 2 and 3 by 2 I cross 4 cross 4. Any doubts in this? Okay, no doubts. Fine. Question 8. So again, Mimo channel estimation build up to the previous 2 questions, and we are asked what is the LMMSE estimate of the Mimo channel matrix. Okay, so again in the lectures, this formula has already been derived. So sigma H square X transpose X plus sigma square I inverse X transpose Y. Okay, so this is what we have. And what is X? So we have X is 2 minus 2 to 3 to 1 minus 2 2. Okay, and Y is basically 1 minus 2 1 minus 2 1 3 minus 3 1 minus 2 2 minus 3 minus 1. So right, and we know that sigma H square is minus 6 dB. So we have been doing this today. So this is basically 1 by 4, and sigma square is minus 3 dB, which is half. Okay, so all right, now what is X transpose X? So just a minute. So I think this question was I think the initial questions. Okay, so the X vector is same, but Y vector is different. Okay, so like that. So X transpose X is just a minute. All right, so what you have, so 2, 2, 2 minus 2 minus 2 3 1 2 times 2 minus 2 2 3 2 1 minus 2 2. Okay, and if we solve this, so this will come out to be 16 0 0 18. Okay, this is X transpose X. So basically we'll be plugging the values in this directly. So we have 1 by 4 times this is 2 by 9 0 0 2 by 10. So this is if you solve this entire stuff, sigma H square X transpose X plus sigma square I inverse. Okay, if you solve this, and X transpose Y will come out to be minus 12 minus 7 6 2 6 3, and so this is my X transpose Y, and you will be getting minus 2 by 3 1 by 3 1 by 3 minus 7 by 20 1 by 10 3 by 20. Okay, so this is what you have. This is option B. Right? Any doubts? Feel free to ask. Doubts. Okay. Question 9. So we are now asked what is the error covariance of the LMMSE for the Mimo channel estimation. So we still have X and Y as in the previous question. So error covariance is given as expectation H hat minus H hat minus H transpose. Okay, and as in the lectures, it is X transpose X by R sigma square plus I over R sigma H square inverse. Okay, so we'll just substitute the values in this. So X transpose X is 16 0 0 18 divided by 3 times sigma square is minus 3 dB. So this is half plus 1 0 0 1 times 3, and sigma H square is basically 1 by 4, right? And if you basically solve this, you will be basically having 12 0 0 40 by 3 inverse, and this is basically 1 over 12 0 0 and 3 by 40, and this is option C. Yeah. Any doubts? Okay. Question 10. So again, we are given a Mimo channel estimation, and we need to find out the ML estimate. Okay, so far we are doing LMMSE, but now we have been just asked what is the ML estimate. Okay, so read the question carefully. So this is very straightforward. So this I think we did in week 4 or 5. So X transpose X inverse X transpose Y. That's it. Very straightforward. All right. And what is this? So X transpose X is basically 16 0 0 18 inverse. This is it. And X transpose Y is -12, -7, 6, 2, 6, 3. So if you multiply x and y, you will be basically getting this. Okay. So if you solve this, you get -3/4, 3/8, 3/8, -7/18, 1/9, 1/6. So this is what you have. So this is option D. Okay, any doubts? No doubts? Okay then. So I think that's all for today's class. We solved the problem. So just a reminder, so next class will be last class, and if you have any doubts, you can bring it and we'll discuss. Okay, so any doubt which you have, you can just ask. Okay, then I will stop recording and thank you.
Thank you, sir.